Result today, an equation where all the variables are assumed to be integers. Okay, the x, the d, and the y. Now we're going to also assume that d does not equal to k squared. Let's use another letter. My goodness, we're running out of letters here. So we don't want d to be a perfect square. I guess we'll use m if you want, where m is another integer. Now, it doesn't take much to verify that if d is a perfect square, that the only solutions are the trivial solutions. That would be x equals plus or minus 1 and y equals 0. That's something that's not hard to verify. So we're going to assume that d is not a perfect square. Now, what we're trying to do right here is generate an infinite number of solutions based on a known solution. We're given that a comma b is a solution to this equation, which is called Pell's equation. And we want to show a way to generate an infinite number of integer solutions. Now this expansion, I love the notation right here. Notice that a and b is the solution, and we're expanding it to an integer k. Of course, I guess technically it might hold for k equals 0, but we're thinking that k is, we're assuming that k is, a natural number 1, 2, so on. Okay, so k is a natural number, and this is a binomial expansion. Now again, I love the notation here quite a bit, because when you expand this out, you're going to get different constants based on the value of k. So the subscript k is not only identifying, but it's indicative of the fact that depending on the value of k, of course, the values of these constants are going to change. Okay. Now what we want to show is that these two constants are actually solutions to this equation. That is, in other words, we're trying to show that a sub k comma b sub k. I'm using the upper and lower case here. I know it's a little cumbersome here, but you run out of letters in a hurry when you're doing this stuff. But so you have a sub k. We're trying to show that this is also a solution. Okay, again, we're given little a comma b is a solution, and we're going to do some work here that shows that a sub k, b sub k is also a solution. Notice it fits this form right here. Okay, now the hardest part for me was realizing that this was an important step right here. Now this may look obvious, but to me it's not completely obvious. The reason, at least in my mind, why you can just reverse the sign here is that if you just take a look at all the, let me just write this out, minus b root d raised to an odd power. Okay, raised to an odd power. Let me go ahead and write this. Odd, right? ODD, raised to an odd exponent. Now, it's pretty clear that the minus sign gets preserved here. But also, you're always going to get the even part is just going to make the square root of d come out to be an integer, right? So this is always going to be in the form some multiple. We can use n if you want to. It's going to be minus n, where n's an integer, positive integer, I guess, and the minus sign stays, right, times root d. Okay, I hope that's readable there. That's supposed to be minus n times root d that is equal to all of this. And you see, that's why you would preserve the minus sign. The minus sign, you could expand it out to see it, but I think pretty sure everybody's comfortable with why this holds up, right? The even part of the odd number would produce the integer, and then you would have 1 root d left over like that. Okay, and so that's why we can make the assumption that the minus sign right here translates directly from this. Okay, now notice that if this were even, that would just contribute to the integer portion here. You see, all the even exponent terms in this expansion will generate integers, right? Because when you're squaring the square root of something, you get an integer. But all the odd terms in the expansion are going to produce a term like this, which will actually be right here. Okay, it'll actually be absorbed right here. Okay, so I hope that makes sense and it wasn't too confusing, because it bothered me at first why it was true. Okay, now the rest of it's actually pretty straightforward. Notice that this form is the difference of two squares. Okay, and it's these two objects right here that we've just talked about. Okay, so the rest of it is just laws of exponents, and I won't say, there's not much to say here. It works out very nicely. If we substitute on the right-hand side, in other words, this is just direct substitutions right here. A sub k minus b sub k root d is actually equal to this, and the same for the plus version. So I just wrote it down. Okay, so just replace these with what they're equal to. This is just laws of exponents, right? You can combine this into a single, just properties of exponents is what's happening from this step to this step. And of course, this step right here demonstrates that this whole thing is still equal to 1 because a comma b is a solution to the original. Remember, let's go back. A comma b is a solution to this equation right here, which is what the equation we're dealing with, right? And so what we get is that since ab is a solution to the original equation, we get 1, that this entire expression is equal to 1 just by the algebra here and the difference of two squares. So we're done with that part of the problem. We've actually proved that AK comma BK is a solution to this original equation. And I'm not keeping it on the same screen for you. Sorry about that. But anyway, we have that completes the proof. So we can write QED. Now I want to show you a concrete example of this, because a lot of notational fluency. It took me quite a while to do this video just because it's all about the notation, really. It's very little heavy-duty thinking going on. It's just coming up with decent notation. So we've established that AK A sub k comma A sub b is a solution. Or I'm sorry, b sub k. A sub k comma b sub k is a solution and again it's a solution to this original equation. Now I think it's kind of neat. It was ginned from a known solution. Okay, so you do have to come up with a concrete solution to this before you can generate an infinite number of solutions, and there will be an infinite number of solutions since the natural numbers are an infinite set, right? For each natural number, you can produce a solution that is a kind of a function of k, the coefficients at least, or the coordinates. Okay, so good for that. Now this is an example. Y'all right here, this makes it kind of nice. You kind of can see what's going on here when the numbers get substituted in. But 10 comma 3 is certainly a solution, right? Because this would be 100 minus 11 times 9, which is 100 minus 99, which is 1, right? So 10 comma 3 is a solution. So we expand it out, and I'll write you just the notation here. This is what we proved. We just finished proving this statement in kind of a hopefully not too cumbersome way. All right, we just finished proving this result, where the result of this expansion generates the new solutions, okay? And here's a concrete example here, folks. This is the, you guys have seen this. This is in the form a plus b cubed right here. A plus b cubed, and then you get the familiar coefficient pattern of 1, 3, 3, 1. A plus b cubed is the left-hand side. And again, I won't write out the entire expansion, but you know that you get a cubed right here, and then this would be 3a squared b, this would be 3ab squared, and this would be a b cubed right here, okay? And it all works out very nicely, and you can rest assured, you know, you can substitute this calculator if you want, but this is guaranteed to work out. It's kind of nice. A lot of algebra leads to this. This would be a fairly difficult thing to compute, you know, if you were just doing it by hand. But based on the algebra, there's no real spots for mistakes in the algebra, I don't think, and I double-checked it. This has to be true. This is a numerical example of this truth. And again, we just proved this statement and this is a numerical example. Let me know what you think. Hope you enjoy.